Hello, in this lecture we will answer on two questions. In the first question, we will find out the area of this semicircle that is inscribed by a quarter circle, and in the second question, we will find out the size of this angle theta, that is one angle of the right triangle ABC. Okay, and we will answer on both questions in two different methods. So we'll start with the first question, and in the first method in the drawing we have a quarter circle. We know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. So we will define the center of the semicircle as point C, and this will be point A, B, C, this will be point E, this will be point F, and this will be point G. From the center of the semicircle, we will draw radius to the point of tendency of tangent AB with this semicircle. Actually, we have a rule that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. That is to say, if we have a circle and we have tangent AB, this tangent AB is tangent to the circle at this point M. Point M is the point of tendency, and the center of the circle is at point O. So OM will be the radius of the semicircle. So we'll define it as R. And according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. I'm reading rule number 1 again. A tangent to a circle is perpendicular to the radius drawn to its point of tendency. So what is the meaning of rule number 1? The meaning of rule number 1 is that whenever you have a radius, like in this drawing, the radius OM, that is the radius of this circle, whenever the radius is drawn to the point of tangency, like in this case, the radius OM, it is drawn to point M, that is the point of tangency of tangent AB with this circle, then according to rule number 1, the tangent AB will be perpendicular to the radius OMO. That is to say, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, so a tangent to a circle, that is to say tangent AB, is perpendicular to the radius drawn to its point of tangency. So the tangent AB is perpendicular to the radius MO that is drawn to the point of tangency, that is point M. So whenever the radius is drawn to the point of tangency, then the tangent AB will be perpendicular to the radius MO. That is to say, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. So according to rule number 1, because of the fact that the radius CE is drawn to the point of tendency, that is to say it is drawn to point E, that is the point of tendency of tangent AB with this semicircle, then whenever you have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to this radius EC. So AB is perpendicular to EC, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. According to rule number 1. Likewise, from the center of the semicircle, that is to say from point C, we will draw the radius that is drawn to the point of tendency, that is to say here this radius OC, the radius OC or CO, the radius CO, it is drawn to the point of tendency, that is to say, it is drawn to point O, that is the point of tendency of tangent BH. Tangent BH, this tangent is tangent to the semicircle at point O. Point O is the point of tendency. So whenever you have a radius that is drawn to the point of tendency, like in this drawing, the radius CO is drawn to the point of tendency, that is to say it is drawn to point O, then the tangent BH will be perpendicular to the radius CO. Again, BH is perpendicular to OC, That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. And we also know that because of the fact that AB edge is a quarter circle, then this angle must be equal to 90 degrees. Angle AB edge must be equal to 90 degrees. So actually, inside quadrilateral ECBD, inside this quadrilateral, we have 3 right angles. Okay? Inside quadrilateral ECBO, inside quadrilateral ECBO, we have 1, 2, 3 right angles, and the sum of 3 right angles is 3 times 90, it is equal to 270 degrees, plus the size of the fourth angle, that is actually angle ECO. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here, we will subtract 270 degrees from this equation, and we will get that the missing angle, angle ECO, is equal to 360 degrees minus 270 degrees, it is 90 degrees. Okay, so we found out that the missing angle equals to 90 degrees, so this angle is a right angle. So actually we found out that quadrilateral ECBO has 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle. So I write it down that quadrilateral ECBO must be at least a rectangle because it has 4 right angles. Okay? And we also have the rule that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ECBO, EC equals to BO, EC equals to BO, according to the rule that the opposite sides of a rectangle are equal to each other. But we know that EC equals to R, it is the radius of the semicircle. EC equals to R. So from this equation, R equals to EC equals to BO, we will derive that BO is also equals to R. BO is also equals to R. So we can write here that BO is equal to R. Likewise, because of the fact that the opposite sides of a rectangle are equal to each other, we will derive that CO equals to EB. CO equals to EB. But CO equals to R, it is the radius of the semicircle. CO equals to R. So from this equation R equals to C, O equals to EB, we will derive that EB is also equals to R. EB equals to R. So actually we found out that all the sides of quadrilateral ECBO are equal to each other, and all of its angles are equal to 90 degrees. Therefore, we can conclude from it that quadrilateral ECBO is a square. Quadrilateral ECBO is a square. Okay. We will find out, we will connect together points B and C by a straight line. BC is the diagonal of square ACBO. And we will focus on the right triangle BOC in order, on the right green triangle BOC, in order to find out the length of diagonal BC. And we use the Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, BC square equals to BO square plus CO square. In the right triangle CBO. By Pythagoras theorem. PT is the abbreviation for Pythagoras theorem. So BC square equals to BO square plus CO square. So BC square equals to BO square. BO is R, so BO square is R square plus CO square. CO equals to R, so CO square will be equal to R square. So in conclusion, we found out that BC square equals to R square plus R square. That is to say, BC square equals to R square plus R square is 2R square. Here we'll take a root out of this equation and we get that BC equals to the square root of 2R. BC equals to square root of 2R. That is the length of diagonal BC. It is equals to square root of 2R. In the next step, we will extend the diagonal BC until it touches the semicircle at this point. And we'll define the touching point of the extended BC with the semicircle as point S. What is the length of CS? The length of line segment CS will be equal to BS minus BC. BS minus BC is the length of line segment CS. BS is the radius of the quarter circle that is equal to 3 units. and BC is the length of diagonal of the square that is square root of 2r. So in conclusion, we found out that CS equals to 3 minus BC that is square root of 2r. Okay, CS equals to 3 minus square root of 2r. So we can write here that CS equals to 3 minus square root of 2r. Okay. In the next step, we will complete the quarter circle to a circle. So here we completed the quarter circle to a circle. From the center of the quarter circle, we will extend the diagonal BC by a straight line until it touches the circle at this point. We define the touching point of the extended line segment BC with the circle as point M. Because of the fact that B is the center of the quarter circle, therefore M and B will be equal to the radius of the quarter circle, that is 3 units. Okay? And we have another rule that is related to two chords that intersect with each other inside a circle. Okay, so if we have two chords inside a circle that intersect with each other, then we have a special rule that is related to the relationship between their parts, the relationship between the parts of the two chords. In this circle we have two chords that intersect with each other. So this is chord AB. Chord AB intersects with chord CD. And the intersection point between those two chords is at this point, point O. Then the following relationship exists between their parts. According to the rule, AO times OB is equal to CO times OD. Okay, so in any circle, if two chords intersect with each other and the intersection point in this case is at point O, then the following formula is true, that AO times OB equals to CO times OD. So we can implement this rule in our drawing, because in our drawing we have chord MS that intersects with chord FG at point C. Point C is the intersection point between chord MS and chord FG. Therefore, according to the rule that I mentioned, MC times CS will be equal to FC times CG. I'll repeat again. Chord MS intersects with chord FG, and the intersection point is at point C. Therefore, according to the rule that I mentioned, MC times CS equals to FC times CG. Okay, MC times CS equals to FC times CG. MC is equal to 3 plus square root of 2R. Times CS. We already found out that CS equals to 3 plus square root of 2R. And it is equal to FC. Here FC is the radius of the semicircle, that is to say it is equal to R. And CG is also the radius of the semicircle, that is to say it is also equal to R. Therefore, FC times CG is R times R, that is R squared. So I found out that 3 times square root of 2R times 3 minus square root of 2R equals to R squared. Here we will find out the value of this expression by the trigonometric identity that says that A plus B times A minus B equals to A squared minus B squared. In our specific case, A equals to 3 and B equals to square root of 2R. Therefore, here A squared is 3 squared, that is 9, minus B squared, minus B squared. B is square root of 2R, so B squared will be equal to square root of 2R squared, and square root of 2 squared is 2, and it is also, we have to multiply it by R squared. Okay, square root of 2R squared is square root of 2 squared, that is 2 times R squared. So in conclusion, we found out that this expression 3 plus square root of 2R times 3 minus square root of 2R equals to 9 minus 2R squared, that is equal to R squared. Here we will add 2R squared to this equation, and we will get that 9 equals to 2R squared plus R squared, it is 3R squared. We will divide this equation by 3, and we get that r square equals to 9 over 3, that is 3. So we found out that r square equals to 3. And we know that the area of a circle is pi r square. And because of the fact that the area of a circle is pi r square, when r is the radius, then the area of the semicircle will be equal to half of it. That is to say, the area of this semicircle will be equal to pi r square over 2. Okay, pi r square over 2. That is the area of the semicircle. The area of the semicircle equals to pi r square over 2. R square equals to 3. So it is pi, r square is 3 over 2. So we actually found out that the area of the semicircle equals to 3 pi over 2 square units, or in terms of numbers it is 3.71 square units. Okay? I repeat again, the area of the semicircle, the area of this semicircle that is inscribed by the quarter circle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first method. In the next step, I will present to you how to find out the area of the semicircle, this semicircle, according to the second method. In the second method, we will use all the things that we have already found out in the first method. So here we know that ACOD is a square. We know that it is a square. Okay. FC is the radius of the semicircle. CG is also the radius of the semicircle. And from point O, we will join points O and G together by a straight line. OG is the radius of the quarter circle. That is to say, it is equal to 3 units. We join points O and F together by a straight line. OF, it is also the radius of the quarter circle. That is to say, it is equal to 3 units. We actually know that O is the center, point O is the center of the quarter circle, and because of the fact that point O is the center of the quarter circle, therefore the radius of the quarter circle will be OF. That is actually exactly the definition of a radius. Any line segment that it starts from the center of the circle and ends at any point on the circle itself, it is defined as a radius. Therefore OF, it is the radius of the quarter circle, that is to say it is equal to 3 according to what is given us the question. Likewise, from the same reason, OG will be also the radius of the quarter circle, that is to say it will be equal to 3 units. And we have already found out that the diagonal OC of the square it is equal to square root of 2r, when r is the radius of the semicircle, and here FC is also the radius of the semicircle. We will implement the Pythagoras theorem, but before that I will present to you a new rule according to the new rule. Rule number 2. The median to the base in an isosceles triangle is perpendicular to the base. So I read rule number 2 again. According to rule number 2, the median to the base in an isosceles triangle is perpendicular to the base. So I will copy the isosceles triangle FOG in this new page. So this is the isosceles triangle FOG. You know that OF equals to 3 units and OG is also equals to 3 units. Those two sides are the radiuses of the quarter circle. For that reason, triangle FOG is an isosceles triangle. OC is the median to the base. Why OC is the median to the base? Because of the fact that it bisects the base to two equal parts. FC equals to CG equals to R. It is the radius of the semicircle. And according to rule number 2, the median to the base, that is to say OC is the median to the base in an isosceles triangle, in triangle OFG, that is an isosceles triangle because of the fact that OF equals to OG. So OF equals to OG. Those are the two sides of the isosceles triangle, triangle OFG, while FG is the base of the triangle. So the median to the base, the median OC to the base FG, in an isosceles triangle, in triangle FOG, that is an isosceles triangle, is perpendicular to the base. So the median OC is perpendicular to the base FG. OC is perpendicular to FG, that is to say, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Okay? The median to the base OC is perpendicular to the base FG. OC is perpendicular to FG, that is to say this angle equals to 90 degrees and this angle will also equal to 90 degrees. Okay? Therefore, according to rule number 2, we get that the median OC to the base FG is perpendicular to the base, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees because of the fact that the median OC to the base FG is perpendicular to the base. That is to say, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. So in the next step, we will focus on the right triangle OCF. We will implement the Pythagoras theorem on this right great triangle OCF. Okay, so we will have the right triangle OCF. So this is the right triangle OCF. We will implement the Pythagoras theorem on the right triangle OCF. By PT is information for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the slopes of the perpendiculars. So here we get that OF squared is equal to OC squared plus FC squared. OF is equal to 3, so OF squared is 3 squared, that is 9. And it is equal to OC squared. OC is square root of 2r, so OC squared is 2r squared plus FC squared. FC is r, so FC squared is r squared. So we found out that 9 equals to 2r squared plus r squared, that is 3r squared. We divide this equation by 3 and we get that r squared equals to 9 over 3, that is 3. So we found out that r squared equals to 3 units. And the area of the semicircle, it is equal to pi r squared over 2, that is half the area of a circle. So it is pi times r squared is 3 over 2. Or it is 3 pi over 2 square units. Or in terms of numbers, it is equal to 4.71 square units. Okay? And that is the answer to the question according to the second method. So we actually finished. I'll repeat again. The area of this semicircle that is inscribed by the quarter circle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 3.71 square units. So we finished with the first question. In the next step, I will present to you how to find out, in the next step, I will present to you the second question. In the second question, we have the right triangle, triangle ABC. We know that the side BC of the right triangle, triangle ABC equals to 6 units. We also know that AE is equal to EC, and DE is perpendicular to AC, that is to say angle DEC equals to 90 degrees and angle DEA equals to 90 degrees also. And we want to find out the value of this angle, angle theta. The value of angle BAC, that is equal to theta. Okay, so we start with the first method. In the first method, we will define angle ACB as alpha. Because of the fact that triangle ABC is a right triangle, and this angle equals to alpha, angle BAC equals to theta, this angle equals to theta, that is the angle that we are looking for. So this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right angle triangle ABC to 180 degrees. Here 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. Therefore, this angle ACB equals to 90 degrees minus theta, and according to our definition, it is equal to alpha, so therefore, in conclusion, alpha equals to 90 degrees minus theta. So we can write down that angle alpha equals to 90 degrees minus theta. Here we will subtract theta from this equation, and we will add theta to this equation, and we will subtract alpha, and we will get that theta equals to 90 degrees minus alpha. Okay. Here actually, if we focus on the right triangle, triangle DEC, then this angle DEC, will be equal to 90 degrees minus alpha. So this angle equals to 90 degrees minus alpha. And 90 degrees minus alpha is theta. So we can write here that this angle equals to theta. But before that, from point E, we will draw perpendicular on BC. I repeat again, from point E, we will draw perpendicular on BC. So this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point E and BC as F. So here we actually have the right triangle, triangle FEC. In the right triangle, triangle FEC, angle FEC, if this angle equals to alpha, then angle FEC will be equal to 90 degrees minus alpha. Okay, it is equal to 90 degrees minus alpha. That is actually theta. We know that angle DEC equals to 90 degrees according to what is given as the question. So 90 degrees minus this angle, that is 90 degrees minus alpha, will be equal to angle DEF. I will repeat again, the missing angle, angle DEF, angle DEF, it is equal to 90 degrees, this angle, angle DEC, that is actually 90 degrees, minus the size of this angle, that is 90 degrees minus alpha. So here angle DEF equals to 90 degrees minus 90 degrees plus alpha. So we found out that the missing angle DEF equals to alpha. The missing angle DEF equals to alpha. So in the right triangle EFD, we know that one angle is equal to alpha. So the other angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right triangle FEC to 180 degrees. This angle must be equal to 90 degrees minus alpha. But here 90 degrees minus alpha is theta. So we can write down that this angle equals to theta. And we will define DF as X, we will define FE as Y, we will define AE as A, and because of the fact that AE equals to EC, EC will be also equal to A. And we will prove that that triangle ABC, the big right triangle, is similar to triangle EFC. I'll repeat again. We'll prove that the right triangle ABC is similar to the right small triangle EFC. So triangle ABC, the right big triangle, is similar to the small right triangle EFC. So why those two triangles are similar to each other? First of all, both of them have this angle that is equal to 90 degrees. So angle ABC, this angle is equal to this angle that is actually angle EFC, and both angles are equal to 90 degrees. So angle ABC equals to angle EFC equals to 90 degrees. In addition, this angle is a common angle, it belongs to both triangles. So we can write down that angle ACB of triangle ABC is equal to angle ECF of this triangle. So we actually can say that the angle equals to itself because it is a common angle. So angle ACB equals to angle ECF is a common angle. I'll repeat again, angle ACB is exactly the same angle as angle ECF. Okay, but I wrote it like that in order to emphasize that this angle belongs to both triangles. Okay, it belongs to triangle ABC. In triangle ABC is the angle ACB, and in triangle ECF it is angle ECF. So the angle equals to itself. And the third angle, those two angles are equal to each other, they are both equal to theta. So angle BAC this angle in triangle ABC is equal to angle FEC, and both angles are equal to theta. I'll repeat again. Angle BEC equals to angle FEC, and both angles are equal to theta. So we proved that all three angles in triangle ABC congruent to all three angles in triangle EFC. Both those two angles are equal to theta, both those two angles are equal to 90 degrees, and this is a common angle. Therefore, we proved that triangle ABC is similar to triangle EFC according to angle similarity rule. I will write it down. We proved that triangle ABC is similar, this is the sign of similar, to triangle EFC according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over AC in triangle ABC is equal to EF over AC in triangle EFC. I repeat again, from the fact that triangle ABC is similar to triangle EFC, we conclude that AB over AC equals to EF over AC. AB equals to 6, and AB is the missing variable, of course, so AB equals to AB, AC equals to A plus A, that is to say to 2A, and it is equal to EF equals to Y according to our definition, over EC equals to A. So in conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. Here we have A on both sides of equation number 1, so A will get cancelled, and we will multiply this equation number 1 by 2, and we will get that according to equation number 1, AB is equal to 2Y. AB equals to 2Y, so we can write here that AB equals to 2Y. In the next step, but before that, if we focus on the right triangle EDF, according to the Pythagoras theorem, x squared plus y squared equals to 2 squared. So in the right triangle EDF, by PT, Pythagoras theorem, we will get that x squared plus y squared equals to 2 squared, that is 4. Okay, we found out that in the right triangle EDF, according to the Pythagoras theorem, x squared plus y squared equals to 4. In the next step, we will prove that the right triangle EDF is similar to the big right triangle ABC. Why those two right triangles are similar to each other? So we'll focus on the right triangle ABC, the big right triangle, and the right small triangle EFD. We will prove that the right triangle EFD is similar to the right triangle ABC. Why they are similar to each other? First of all, both those two angles, they are right angles. That's to say they are equal to each other. So angle ABC in triangle ABC is equal to angle EFD in triangle EFD, and both angles are equal to 90 degrees. I repeat again. Angle ABC equals to angle EFD, and both angles are equal to 90 degrees. They are right angles. Both those two angles are equal to theta, therefore they are equal to each other. So angle BAC in triangle ABC is equal to angle FDE in triangle FDE, and both angles are equal to theta. Angle BAC equals to angle FDE equals to theta. And finally, both those two angles are equal to alpha, therefore they are equal to each other. So angle FED or angle ACB in triangle ABC is equal to angle FED in triangle FED, and both angles are equal to alpha. Angle ACB equals to angle FED, and both angles are equal to alpha. Therefore, we proved that all three angles of triangle ABC correspondingly equals to all three angles of triangle EFD. Both those two angles are equal to alpha, both those two angles are equal to theta, and both those two angles are equal to 90 degrees. Therefore, we proved that the right triangle ABC is similar to the right triangle EDF, triangle ABC is similar to the right triangle EDF according to angle similarity rule. And from the fact the two triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that AB over BC in the right triangle ABC is equal to DF over EF. DF over EF. I'll repeat again. From the fact that triangle EFD is similar to triangle BC, we conclude that AB over BC equals to DF over EF. AB equals to 2y, BC equals to 6 units, this is given as the question, and it is equal to DF df equals to x, ef equals to y. So in conclusion, I found out that according to equation number 3, two y over 6 equals to x over y. Here we will divide the numerator and the denominator of this side of equation number 3 by 2, and we get that according to equation number 3, y over 3 is equal to x over y. Here we will multiply by, we will cross multiply this equation number 3, and we get that according to equation number 3, y squared equals to 3x. But according to equation number 2, we have already found out that x squared plus y squared equals to 4. So we can substitute y squared in this equation number 2, by 3x. Because according to equation number 3, yx equals to 3x. We'll do it now and we get that x squared plus y squared and y squared equals to 3x according to equation number 3. It is equal to 4. So here we subtract 4 from this equation and we get the quadratic equation that x squared plus 3x minus 4 equals to 0. So this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here a, b and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X it is actually equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. And the variable that we are looking for is x, so x it is equal to minus b, b equals to 3, so minus b is minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, times c, that is minus 4, over 2a. 2 times a is 1, so 2 times 1 is 2. So in conclusion, we found out that x equals to minus 3 plus minus, here minus 4 times minus 4 is plus 16, 16 plus 9 is 25, so inside the root we have 25 over 2. So here the square root of 25 is 5, so we get that x equals to minus 3 plus minus square root of 25 is 5 over 2. So here we will have two solutions that are possible for x. The first solution for x is that x equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8. Minus 8 over 2 is minus 4. So we found out that x equals to minus 4, or x1, But here you can see that x is the length of side DF of the right triangle, triangle EDF. So x is a length, it must be a positive number. So because of the fact that x is a length, it must be a positive number. Therefore, x cannot be a negative number. So we cancel the solution and we left only with the second solution, x2. It is equal to minus 3 plus 5 over 2. Minus 3 plus 5 is 2 and 2 over 2 is 1. So we found out that x equals to 1, x2 equals to 1. Now I will copy the right triangle, triangle EDF, and we will implement the, I will copy the right triangle, triangle EDF, and we will find out the cosine theta, the value of cosine theta in this right triangle. So we have here triangle, the right triangle, triangle EDF. This is the right triangle, triangle EDF. In the right triangle, triangle EDF, we know that cosine theta equals to df over de. df equals to x, that is equal to 1, de equals to 2. In conclusion, we found out that cosine theta equals to 1 over 2, and when cosine theta equals to 1 over 2, theta itself will be equal to 60 degrees. So we found out the answer to the question is that the value of angle theta, or the size of angle theta, here it is equal to 60 degrees. That is the answer to the question. We finished with the first method. In the next step, I will present to you how to find out the size of angle theta according to the second method. In the second method, we will define this angle ACB as alpha, as we did in the first method. We actually know that AE is also equals to EC. So we define AE as A, as we did in the first method. EC will be also equal to A because of the fact that they are equal to each other. So here in the right triangle, triangle ABC, I will copy the right triangle, triangle ABC. Here we know that because of the fact that this angle is theta, then this angle must be equal to 90 degrees minus theta. So alpha equals to 90 degrees minus theta, exactly as we did in the first method. So in the right triangle, triangle ABC, I copied the right triangle ABC in this new page. Here we can see that in the right triangle ABC, cosine theta cosine alpha equals to BC over AC. Okay, BC equals to 6, AC equals to 2A. 6 over 2A, we will divide both the numerator and the denominator by 2. 6 over 2 is 3, 2 over 2 is 1. So it is, in conclusion, we found out that cosine alpha is equal to, according to equation number 1, equals to 3 over A. Cosine alpha equals to 3 over A. Here we can multiply equation number 1 by A, and then we divide it by cosine alpha, and we get that according to equation number 1, A equals to 3 over cosine alpha. In the next step, we will focus on the right triangle EDC. I will copy the right triangle in a new page, and we will focus on this right triangle. So this is the right triangle EDC that I copied from the original drawing. Here, in the right triangle EDC, what is the value of tangent alpha? This will be equation number 2. Tangent alpha it is equal to DE over EC. D equals to 2 according to what is given as the question, and EC equals to A. In conclusion, we found out that according to equation number 2, tangent alpha equals to 2 over A but according to equation number 1, we have already found out that A equals to 3 over cosine alpha. That is to say, we can substitute A in equation number 2 by 3 over cosine alpha. We'll do it now, and we'll get that according to equation number 2, tangent alpha equals to 2 over A, and A, according to equation number 1, is 3 over cosine alpha. So according to equation number 2, we found out that times alpha equals to 2 times cosine alpha over 3. Tangent alpha is equal to sinus alpha over cosine alpha, so we'll substitute tangent alpha by sinus alpha over cosine alpha, and we get that sinus alpha over cosine alpha is equal to 2 times cosine alpha over 3. Here we'll cross multiply this equation number 2, and we get that according to equation number 2, three times sinus alpha is equal to 2 times cosine square alpha. Okay, we have the trigonometric identity that states that sinus square alpha plus cosine square alpha equals to 1. Here we'll subtract sine square alpha from this trigonometric identity, and we get that cosine square alpha equals to 1 minus sine square alpha. Now we'll substitute cosine square alpha in equation number 2 by 1 minus sine square alpha, and we get that according to equation number 2, three times sine alpha equals to 2 times cosine square alpha, and cosine square alpha according to this trigonometric identity it is equal to 1 minus sine square alpha. We will open the brackets on this side of equation number 2, and we get that according to equation number 2, three times sine alpha equals to 2 times 1 is 2 minus 2 times sine square alpha. We will add 2 sine square alpha to this equation, and we will get that 2 sine square alpha plus 3 sine alpha equals to 2. Here we'll subtract 2 from this equation number 2, and we'll get that according to equation number 2, two sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have a quadratic equation, and the solution to this quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 2, the coefficient b equals to 3, and the coefficient c equals to minus 2, and the variable that we are looking for, that is to say x, is equal to sinus alpha. So we put the data inside the formula for x, and we will find out the value of the values of sinus alpha that is equal to x. So we do it now, and we get that sinus alpha equals to minus b. B is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 2, times c is minus 2, over 2a. 2 times 2 is 4. A is 2, so 2 times 2 is 4. Here we get that sinus alpha equals to minus 3 plus minus. Minus 4 times 2 is 8. Minus 4 times 2 is minus 8. And minus 8 times minus 2 is plus 16. 16 plus 9 is 25 over 4. And the square root of 25 is 5. So here we will have two solutions that are possible for sinus alpha. Sinus alpha will be equal to minus 3 plus minus 5 over 4. The first solution for sinus alpha is that minus 3 minus 5 over 4, minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2. But because of the fact that the function sinus alpha can receive values that are ranging between minus 1 to plus 1, and minus 2 exceeds this range of values that sinus alpha can receive. That is to say, sinus alpha can never be equal to minus 2, because sinus alpha can receive values, can accept values from minus 1 to plus 1. Therefore, this solution is an incorrect solution. We will cancel this solution, and we're left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. So sinus alpha equals to 1 over 2. Sinus alpha equals to 1 over 2. So if sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. And here we know that alpha equals to 90 degrees minus theta. Here you can see that alpha equals to 90 degrees minus theta. So we substitute alpha by 30 degrees, and we get that 30 degrees equals to 90 degrees minus theta. Here we will add theta to this equation, and we will subtract 30 degrees, and we will find out that angle theta equals to 90 degrees minus 30 degrees, that is actually 60 degrees. So we found out that the missing angle theta, it is equal to 60 degrees, exactly as we found out in the first method. Okay, so we finished with the second method of the second question. In the next step, I will summarize the lecture. Okay. We'll start with the first question. In this question, we have a semicircle that is inscribed by a quarter circle. We know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of the semicircle. Okay. First of all, I presented to you a new rule, that is rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So according to rule number 1, in this case we have tangent AB that is tangent to this circle is point M. Point M is the point of tendency. And according to rule number 1, a tangent to a circle, that is to say AB, is perpendicular to the radius drawn to its point of tendency. AB is perpendicular to the radius OM, and AB will be perpendicular to the radius whenever AB will be perpendicular to the radius OM whenever the radius OM it is drawn to the point of tendency. Because of the fact that the radius OM it is drawn to the point of the tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. Therefore, the tangent AB will be perpendicular to the radius MO. AB is perpendicular to MO, that is to say this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, so whenever you have a radius that is drawn to the point of tendency, like in this drawing, then the tangent will be perpendicular to that radius. In this case, AB perpendicular to MO. So we can implement rule number 1 in our drawing. C is the center of the semicircle. From point C, we draw radius to the point of tendency, that is actually point E. Point E is the point of tendency of tangent AB with the semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the radius CE is drawn to the point of tendency, that is to say it is drawn to point A, that is the point of tendency of tangent AB with this semicircle. Therefore, according to rule number 1, the tangent AB will be perpendicular to the radius EC. AB is perpendicular to EC, that is to say this angle equals to 90 degrees and this angle equals to 90 degrees. Likewise, from point C we draw the radius that is drawn to the point of tendency, that is to say it is drawn to point O, that is the point of tendency of tangent BH with this semicircle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. That is to say, in this case, BH will be perpendicular to the radius OS. BH is perpendicular to OS, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees, according to rule number 1. So we have those two angles that are right angles. This angle EBO, must be equal to 90 degrees because of the fact that ABO is a quarter circle. Therefore, this is actually the middle of the circle. Point B is the middle of the circle, and this angle must be equal to 90 degrees. So we actually found out that in quadrilateral ECBO we have 3 right angles. And the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, this fourth angle, that is actually angle ECO. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation, and we found out that the missing angle ECO, this angle equals to 90 degrees. It is a right angle. Therefore, we actually found out that all the angles inside quadrilateral ECBO are right angles. And any quadrilateral that has 4 right angles must be at least a rectangle. So, quadrilateral ECBO must be at least a rectangle. But we know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ECBO, EC must be equal to BO. EC equals to BO. The opposite sides of rectangle are equal to each other. That is to say, in rectangle ECBO, EC must be equal to BO. But EC equals to R. This is the radius of the semicircle. So EC equals to R. So from this equation, R equals to EC equals to BO, we will derive that BO is also equals to R. BO is also equals to R. Likewise, because of the fact that the opposite sides of rectangle are equal to each other, we will conclude that in rectangle ECBO, CO equals to EB. CO equals to EB, but here CO is equal to R. It is the radius of the semicircle. CO equals to R, so from this equation R equals to CO equals to EB, we will derive that EB is also equals to R. If EB is also equals to R, so we found out that all the sides of quadrilateral ECBO are equal to each other, and all of its angles are right angles. Therefore, we can derive from it that quadrilateral ECBO is not a rectangle but a square. Okay, quadrilateral ECBO is a square. And then we join points B and C together by a straight line. BC is the diagonal of square ECBO. Okay, and we will use the Pythagoras theorem in order to find out the length of BC. According to the Pythagoras theorem, if we focus on the green triangle CBO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CB square equals to BO square plus CO square. Or BC square equals to BO square plus CO square. BC square equals to BO square. BO equals to R, so BO square is R square plus CO square. CO equals to R, so CO square is R square. So in conclusion, we found out that BC square equals to R square plus R square. R square plus R square is 2R square. So in conclusion, we found out that BC square equals to 2R square. We took a root out of this equation and found out that BC equals to the square root of 2R. So we found out that the length of diagonal BC is square root of 2R units. And what is the length of line segment CS? CS will be equal to BC minus CS will be equal to BS minus BC. BS minus BC equals to CS. Okay, CS equals to BS minus BC. BS is the radius of the quarter circle that is equal to 3 units. It is given as the question. BS equals to 3 units, and we just right now found out that BC equals to the square root of 2R. So in conclusion, we found out that CS equals to 3 minus square root of 2R. CS equals to 3 minus square root of 2r. Okay, and then I presented to you a new rule that it is relates to two chords that intersect with each other inside a circle. Here we have two chords, chord AB and chord DC intersect with each other at point O. Point O is the point of intersection between those two chords. And whenever you have two chords that intersect with each other inside the circle, then the following formula is true, or the following relationship exists between their parts. That is to say, AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement this new rule in our drawing. Why? Because in our drawing we have two chords that intersect with each other, but before that we did a construction from the quarter circle. We made a circle, we completed the quarter circle to a circle, and then we extended the diagonal CB by a straight line until it touches the circle at this point. This is point M, is the point, the touching point of the extended CB with the circle. So what is the value of MB? B is the center of the quarter circle, and M is the point on the circle itself. This is exactly the definition of a radius. BM is the radius of the quarter circle, and the radius of the quarter circle equals to 3 units. Therefore, MB will be equal to 3 units, and we know that BC equal to square root of 2r, and CS equals to 3 minus square root of 2r. Therefore, we have one chord that is called MS. MS is one chord. The second chord is called FG, and they intersect with each other at point C. This is the point of that intersection, and according to the rule, that FC is the radius of the semicircle, that is to say it equals to R, and CG is also the radius of the semicircle, that is to say it is equal to also R. And according to the rule that I mentioned, whenever two chords intersect with each other, then the following formula is true, that MC times CS equals to FC times CG. Okay, according to the rule that I mentioned, MC times CS equals to FC times CG. MC equals to 3 plus square root of 2r. Okay, CS equals to 3 minus square root of 2r. So MC is 3 plus square root of 2r, CS is 3 minus square root of 2r, FC is r, and CG is r. So it is FC times CG is r times r, that is r squared. Okay, so we have this equation that 3 plus square root of 2r times 3 minus square root of 2r equals to r squared. We solved, we found out the value of this expression according to the algebraic identity that a plus b times a minus b equals to a squared minus b squared. In our specific expression, a is equal to 3 and b equals to square root of 2r. Therefore, a squared minus b squared, a squared is 3, so a squared is 3 squared, that is 9, minus b squared. B squared is square root of 2r squared. Square root of 2r squared is square root of 2, that is 2, times r squared, or 2r squared. And minus b squared will be equal to minus 2r squared. So in conclusion, we found out that the value of this expression equals to 9 minus 2r squared, that is equal to r squared. We added 2r squared to this equation and we found out that 9 equals to 2r squared plus r squared is 3r squared. We divided this equation by 3 and we found out that r squared equals to 3. And we know that the area of a circle is pi r squared. Therefore, the area of the semicircle will be equal to half of it. That is to say, it will be equal to pi r squared over 2. R squared is 3, so pi r squared is pi times 3. And then we divide it by 2 because it is a semicircle. So it is 3 pi over 2 square units. The area of the semicircle equals to 3 pi over 2 square units. So in terms of numbers, it is equal to 4.71 square units. I'll repeat again. The area of this semicircle that is described by a quarter circle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first method, and then I presented to you how to find out the area of the semicircle according to the second method. In the second method, we have here we used all the things that we've already found out in the first method. So here ACOD is a square, and we already found out that the diagonal of this square is equal to square root of 2r. Then we join together points O and F by a straight line. OF is the radius of the quarter circle, that is to say, it is equal to 3 units because of the fact that it starts from the center of the quarter circle, that is to say from point O, and ends at point F, that is the point of the quarter circle itself. Therefore, OF is the radius of the quarter circle, that is to say it is equal to 3 units. For the same reason, OG is also the radius of the quarter circle, and that is also equal to 3 units. So, triangle OFG is an isosceles triangle because of the fact that side OF equals to side OG equals to 3 units. Okay? Here. And so we know that triangle FOG is an isosceles triangle. FG is the base of the isosceles triangle, and OC is the median to the base. And we have rule number 1 that states that the median to the base in an isosceles triangle is perpendicular to the base. So what is the meaning of rule number 1? The meaning of rule number 1 is that here we have the isosceles triangle, triangle FOG. Triangle FOG is an isosceles triangle because of the fact that FO equals to OG equals to 3 units. And the median to the base FG is OC. Why the median is OC? Because it bisects the base FG into 2 equal parts, R and R. And according to rule number 1, the median to the base is not only bisects the base in an isosceles triangle, but it is also perpendicular to the base. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay? We implemented rule number 1 in our drawing, so we can, according to rule number 1, we can determine that this angle equals to 90 degrees and this angle equals to 90 degrees. So we created here 2 right triangles from the isosceles triangle, triangle FOG. Okay? So if we take the right triangle, triangle FOC, this is the right triangle FOC, we have already found out that the diagonal of the square, it is equal to OC, it is equal to square root of 2r. FC is the radius of the semicircle, that is equal to r. And OC is the radius of the quarter circle, that is equal to 3 units. Okay? And then we implemented the Pythagoras theorem on this right triangle FOC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, OF square equals to FC square plus OC square. OF equals to 3, so OF square is 3 squared, that is 9. And it is equal to OC square. OC is square root of 2r, and OC square will be equal to 2r square plus FC square, that is r square. So in conclusion, we found out that 9 equals to 2r square plus r square. 2r square plus r square is 3r square. That is to say, 9 equals to 3r square. We divided this equation by 3, and we found out that r square equals to 3 units. And the area of the semicircle is pi r square over 2. So pi and r square is 3 over 2. In conclusion, the area of the quarter circle is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. Okay, we finished with the first question. In the next step, I presented to you how to find out the size of angle theta in the right triangle ABC. In the right triangle ABC, we know that side BC equals to 6 units, angle ABC is equal to 90 degrees. Here DF is perpendicular to AC, that is to say, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. DE equals to 3 units in its length, and AE equals to EC. And we want to find out the value of this angle theta. Okay. So we defined angle ACB as alpha, but because of the fact that triangle ABC is a right triangle and this angle equals to theta, then this angle must be equal to 90 degrees minus theta, because it completes the sum of the angles in the right triangle ABC to 180 degrees. Therefore, this angle equals to 90 degrees minus theta, but according to our definition, it is equal to alpha. From that fact, we will conclude that alpha equals to 90 degrees minus theta. Here, alpha equals to 90 degrees minus theta. If we add theta to this equation and subtract alpha, then we will get that theta equals to 90 degrees minus alpha. Then we made a construction. From point E, we draw perpendicular on BC, so this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. And we define the touching point of the perpendicular from point E and BC as F. So we know that, so this is a right triangle. Triangle CEF is a right triangle, and this angle equals to alpha. So this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right triangle EFC to 180 degrees. So what is the size of angle FED? FED will be equal to 90 degrees minus the size of this angle, that is 90 degrees minus alpha. Okay? So angle DEF, this angle will be equal to 90 degrees minus the size of this angle, that is 90 degrees minus alpha. Angle DEF equals to 90 degrees minus 90 degrees minus alpha. We open the brackets here and we found out that angle DEF equals to alpha. So this angle equals to alpha. And we know that DFE is a right triangle. So if this angle equals to alpha, then this angle must be equal to 90 degrees minus alpha. So angle EDF equals to 90 degrees minus alpha, but here we know that 90 degrees minus alpha equals to theta, so we can substitute 90 degrees minus alpha by theta. So this angle equals to theta. Then we define DF as x, EF as y, we define AE as A, and EC as A. Why? Because AE equals to EC, so if A equals to A, then EC must be also equal to A. Then we proved that the right triangle ABC is similar to the right triangle EFC. Okay? I'll repeat again. We proved that the right triangle ABC is similar to the right triangle EFC. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to 90 degrees. Those two angles are also equal to each other, they are both equal to theta. And this angle is a common angle, it belongs to both triangles. So actually we proved that all the angles of triangle ABC is equal to all the angles of triangle EFC. Therefore we proved that the right triangle ABC is similar to the right triangle EFC according to angle similarity rule. Okay, triangle ABC is similar to triangle EFC according to angle similarity rule. From the fact that those two triangles are similar to each other, we will conclude that AB over AC equals to EF over AC. Okay, AB over AC equals to EF over AC. AB is AB, AC equals to A plus A, that is 2A, AC equals to 2A, EF equals to Y, and EC equals to A. So in conclusion, we found out that AB over 2A equals to Y over A. We have A on both sides of the equation, so A will get cancelled. And we multiplied the equation number 1 by 2, and we found out that AB equals to 2Y. AB equals to 2Y, so we can write here that AB equals to 2Y. Then in the right triangle DEF, x squared plus y squared equals to 2 squared. In the right triangle DEF, by Pythagoras theorem, x squared plus y squared equals to 2 squared, that is 4. Then we proved that the right triangle EDF is similar to the right big triangle ABC. Why those two right triangles are similar to each other? First of all, both of them has this angle that is the right angle. Second, both of those two triangles have this angle that is angle theta. And finally, both those two angles are equal to alpha. Therefore, all the angles of triangle EDF can go into all the angles of triangle ABC. Therefore, they are similar to each other according to angle similarity rule. Triangle ABC is similar to triangle EDF according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over BC in triangle ABC, it is equal to DF over EF in triangle EDF. Okay, AB over BC in triangle ABC equals to DF over EF. AB equals to 2y, BC equals to 6, DF equals to x, and DF equals to y. So in conclusion, we found out that 2y over 6 equals to x over y. We divided both the numerator and the denominator of this side of the equation by 2, and we got that y over 3 equals to x over y. We multiplied this equation, and we found out that y squared equals to 3x. Okay? But according to equation number 2, we have already found out that x squared plus y squared equals to 4. So we can substitute y squared in this equation number 2 by 3x. Because y squared equals to 3x. We did it and we got that x squared plus y squared, that is 3x, equals to 4. We subtracted 4 from this equation and we got the quadratic equation that x squared plus 3x minus 4 equals to 0. The general formula for the quadratic equation is ax squared plus bx plus c equals to 0. A, b, c and the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the formula that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. And so we put the data inside the equation for x, and we found out that x equals to minus b is 3, so minus b is minus 3, plus minus b squared, b is 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, and c is minus 4, over 2a. A is 1, so 2 times 1 is 2. Here we have minus 4 times minus 4 is plus 16, and 16 plus 9 is 25, so inside the root we have 25. So in conclusion, we found out that x equals to minus 3 plus minus square root of 25 over 2. The square root of 25 is 5. So in conclusion, we found that x equals to minus 3 plus minus 5 over 2. So here we have two solutions that are possible for x. The first solution is x equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8. Minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. But because of the fact that x is a length, it is the length of side DF of triangle EDF, it must be a positive number. It cannot be a negative number. X is a length, therefore it must be a positive number. X cannot be a negative number. So we cancel this solution. We have to remove the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x equals to 1. So then I copied the right triangle EDF in the new page, and we implemented here the function cosine. This is triangle EDF. X equals to 1, d equals to 2, and df equals to 1. So here cosine theta equals to df over ed. In triangle EDF, cosine theta equals to df over de. df equals to 1, d equals to 2. So in conclusion, we found out that cosine theta equals to 1 over 2, and if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. So we found out that this angle theta equals to 60 degrees. We finished with the first method, then I presented to you how to find out the size of angle theta according to the second method. In the second method, we define this angle as alpha. And because of the fact that in the right triangle ABC this angle equals to theta, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC to 180 degrees. And then AE equals to A, EC equals to A, and here we have cosine alpha in the right triangle ABC, I copied the right triangle ABC in this new page. Here you can see that cosine alpha equals to BC over AC. Cosine alpha equals to BC over AC. BC equals to 6 units, AC equals to 2A. So in conclusion, cosine alpha equals to 6 over 2A. We divided both the numerator and the denominator by 2. 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that cosine alpha equals to 3 over A. We multiplied equation number 1 by A, and then we divided by cosine alpha, and we found out that A equals to 3 over cosine alpha according to equation number 1. Then we focus on the right triangle EDC. In this right triangle, cosine tangent theta will be equal to DE over EC. In the right triangle EDC, tangent alpha will be equal to DE over EC. DE equals to 2 and EC equals to A. So in conclusion, tangent alpha in the right triangle EDC equals to 2 over A. But according to equation number 1, we have already found out that A equals to 3 over cosine alpha. So we can substitute A in equation number 2 by 3 over cosine alpha. We did it, and we got that tangent alpha equals to 2 over A, that is actually 3 over cosine alpha according to equation number 1. And we found out that tangent alpha equals to 2 times cosine alpha over 3. And tangent alpha equals to sinus alpha over cosine alpha. So we substituted tangent alpha by sinus alpha over cosine alpha. And we got that sin alpha over cosine alpha equals to 2 times cosine alpha over 3. Because multiplied this equation, and we found out that 3 times sin alpha equals to 2 times cosine square alpha. Then we have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this equation, and we found out that according to this trigonometric identity, cosine square alpha equals to 1 minus square alpha. So we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We did it, and we got that 3 times sine alpha equals to 2 times cosine square alpha, but cosine square alpha according to this trigonometric identity will be equal to 1 minus sine square alpha. Then we open the brackets here, and we got that 3 times sine alpha equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 times sine square alpha. We added 2 sine square alpha to this equation, and we found out that 2 sine square alpha plus 3 sine alpha equals to 2. We subtracted 2 from this equation, and we found out that 2 sine square alpha plus 3 sine square alpha minus 2 equals to 0. We find out the value of sine alpha according to the solution to a quadratic equation, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the variable x that we are looking for is sine alpha. So we put the data inside the formula for x, and we found out that in this case x equals to sine alpha, so sine alpha equals to minus b. In our specific quadratic equation, the coefficient a is 2, the coefficient b is 3, and the coefficient c is equal to minus 2. So we put the data inside the formula for x, and we found out the values of sinus alpha. X equals to minus b is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9, minus 4 times ac. Minus 4 times a is 2, so it is minus 4 times 2 times c, that is minus 2, over 2a. A is 2, so 2a is 2 times 2, that is 4. Inside the brackets we have minus 4 times 2 is minus 8, minus 8 times minus 2 is plus 16. 16 plus 9 is 25, so in conclusion we found out that sinus alpha equals to minus 3 plus minus square root of 25 over 4. the square root of 25 is 5, so in conclusion we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we have two solutions that are possible for sinus alpha. The first solution is sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So in conclusion we found out that sinus alpha equals to minus 2. It is incorrect solution because the values that sinus alpha can receive is between minus 1 to plus 1, and minus 2 exceeds this range of values that sinus alpha can accept. That is to say, sinus alpha can never be equal to minus 2. Okay, so we cancel this solution and we left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2, and 2 over 4 is 1 over 2. Okay, so we found out that sinus alpha equals to 1 over 2. So if sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. So we found out that alpha equals to 30 degrees, and we only found out that alpha equals to 90 degrees minus theta. Here, alpha equals to 90 degrees minus alpha. Alpha equals to 90 degrees minus theta. So we can substitute alpha by 30 degrees because we found out that alpha equals to 30 degrees, and we got that 30 degrees equals to 90 degrees minus theta. We added theta to this equation and we subtracted 30 degrees, and we found out that theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees is 60 degrees. In conclusion, we found out that the angle that we are looking for, angle theta, it is equal to 90 degrees according to the second method also. Okay? Thank you very much.